Welcome to a quick review of logarithms and exponents. Here we go. I have a couple things for you to consider. Number one. Number two. What's the difference? Well, let's take a look at a table view. And so I'm going to plot some values for x and y. I'm going to do the same for this function here. Okay. By the way, this is a quadratic function. It's a second degree polynomial. And this guy over here is an exponential function. Note the location of the variable. Okay, that's what distinguishes the two, or one of the things that distinguishes the two. The location of the variable. The base is the variable here. The exponent is the variable here. That's why we call them exponentials, because the variable is in the exponent. Okay, this guy's obviously a quadratic. The variable is downstairs at the base. Alright, so let's take a look at some values that would be in this table. So we'll take a look at some common values, -2, -1, 0, 1, 2, and we'll look at the same values for x here. Sound good? So basically what I want to do is I want to take -2, -1, 0, 1, 2, and plug them in for x here. And so I'm going to square -2, I'm going to get 4. I'm going to square -1 to get 1. I'm going to square 0. I'm going to square 1. I'm going to square 4. All right, let's go up a couple more just to get crazy. I'm going to square 3. I'm going to square 4, etc., etc. Okay, and so that's the squared function, right? Let's look over here, and let's do the same thing with these values of x, the same values. And so 2 to the -2 is 1 over 2 squared, which is 1/4. 2 to the -1 is 1 over 2 to the first, which is 1/2. 2 to the 0, or any non-zero number raised to the 0, is 1. 2 to the 1 is 2. 2 squared, 4. 2 cubed is 8, and 2 to the 4th is 16. And so here we have a good little snippet of each particular function's table for some selected values of x, common values of x. So what's the difference? Well, look at how these are increasing. Okay, in particular, look at this exponential function. Each multiple is 2 times 2 the previous, times 2, 1 times 2, 2 times 2, 4 times 2, 8 times 2. Okay, that's not the case here with x squared. This particular illustration shows you what exponential growth means. We're multiplying itself by 2. It's recursive in a sense. So we multiply the previous input by 2 to get the next one. So it's a doubling. You have a constant doubling, a continual doubling. Okay, where that's not the case with this quadratic over here. Nothing's being doubled. We're just raising different numbers to the power of 2. Okay, and of course different patterns do emerge. But what I want to focus on is this exponential. So let's turn the page and kind of think about what that doubling looks like. And here's a general graph of y equals 2 to the x. Okay, goes to the point 0, 1, because 2 to the 0 is 1. We have two asymptotes, one asymptote. As x approaches negative infinity, we have 0. So that means as x is going to negative infinity, 2 to the x is going to 0. So that means y equals 0 is a left-end behavior model. Left-end behavior model. In any event, the domain is all reals, the set of all x such that x is a real number. Right? Ain't no number you can't raise to 2. Can't plug in for this x value. The range, however, is restricted because you can't take 2, a positive number, raise it to any power to turn it 0 or anything less than 0 for that matter. So the range is a set of all y's such that y is positive. Okay. Now what I want to do is find the inverse. And to find the inverse, remember, to find an inverse of a function, and another way of saying that is y to the -1, we switch the x and the y's, and then we solve for y. Alright, so that's just a quick reminder. So if I want to find the inverse of y equals 2 to the x, the exponential function, I'm going to switch the x and the y, so now I get x equals 2 to the y. But now I need to solve for y. Well, how do I do that? Well, that's where logarithms come into play, or one of the places. And so we need logarithms in order to do so. So I'm going to scroll down here and give you the gist with logarithms. So here's how logarithms work. If b to the x equals y, right? B being base to the x power equals y. That can be written as a logarithm of base b, right? These two b's are consistent. Jump over the equal sign of y equals x. Okay, these are equivalent statements, if and only if. Okay, meaning that, and let me give you some colors here, that x goes here, that y goes here, and b being the base goes here. Okay, so those are equivalent statements. So if 2 cubed equals 8, that means log base 2 of 8 equals 3. 2 cubed equals 8. Right? They're the same thing. Okay, and that's what logarithms, one of the things that logarithms gets us. So now, using the same concept, I can take this statement, x equals 2 to the y, and just rewrite it using a logarithm. So the way in which that works is logarithm base 2 of x equals, jump back over the sign, equal sign y. And so these guys are inverses. Log base 2 of x. And so the relationship between y equals 2 to the x and y, the inverse, equals log base 2 of x is that they're inverses. Right? I just showed that to you. And because they're inverses, they're going to be reflections over this line y equals x. All the x and y values are going to be switched. So since 2 to the x goes through 0, 1, this guy's going to go through 1, 0. Right? Since 2 to the x has y equals 0 as a left-end behavior model, this guy's going to have, this guy, its inverse log base 2 is going to pinch towards negative infinity as x is going to 0. Everything gets flopped. Okay, so for the logarithm base 2 of x, which is equal to y, for that function, the domain is the range of its inverse. So the set of all x as long as x is positive. Okay, you can't, if our base is 2 of the logarithm, you can't raise 2 to any power to get any 0 or negative number. You guys might have heard you can't take the logarithm of negative or 0. That's why. As long as we have a positive base, which we always will, so that they're well behaved. Unlike you guys in class. Just kidding, JK. The range, therefore, will be the domain of its inverse, which is just going to be the set of all reals. Okay, so there's a quick little something something for exponential growth and the relationship it has to logarithms. 2 to the x and log base 2 of x are inverses. A problem I'd like for you to consider for tomorrow is this. If you have $1,000, how long in a 0.31 in a 3.1% fund, which is compounded interest annually, to double? Okay, so I'll help you out a little bit. There's a general rule that the principal, the amount we put in, times 1 plus the interest rate, which I'll call r in decimal, to the t, is going to equal how much it's worth now. Okay, so use that and use logarithms to figure out how long it's going to take to double. See you tomorrow. Wubba wubba wubba. Good God. Blah, blah, blah.